Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi guys, we meet again for our physics class module 2, AMT1121, AMT1121. Okay, right now we are covering chapter 2 mechanics, subtopic kinematics. Okay, before we move to our new session today, let's take a while to revise what we have learned in the last session in kinematics. So previously we studied about 5 physics quantities, that is distance, displacement, speed, velocity and acceleration lah. So we know distance ataupun jarak is a scalar quantity ataupun jarak scalar quantity. Displacement is seseran, is a vector quantity where they have the magnitude and direction. And then another one is speed. Speed is a scalar quantity, rate of change of distance, kadar perubahan jarak. And then velocity, rate of change of displacement. Velocity adalah vector quantity where have magnitude and direction. Another one is acceleration ataupun pecutan, is a vector quantity which have magnitude and direction. Okay, we try to continue our topic today, that is periodic motion. Okay, some masses move from one point to another point. Some move from round and round. This motion has been described as a translation or rotational. Some masses move from one point to another point, then back to the original point and continue to do it respectively. Periodic motion, this means that any object has been displaced from its original position to another position and back to its origin position. As per the slide, the time during which the mass moved away from and then return to its original position is known as the time period, and motion is known as periodic. So that is the definition of periodic motion. Banyak mechanism, a lot of mechanism or component behave in this manner, such as spring, pendulum, elastic ball, all will come back to its origin position after has been replaced from its original position. Okay, we see an example. Okay, pendulum. If a pendulum is displaced from its stationary position, keadaan asal, and released, it will swing back toward that position. We see in this picture, if pendulum we display from its original position. Example, the original position is at the center lah. So we pull apart to one position and release it, and then it will swing back and back to its original position, towards the position. On reaching it, however, it will not stop because it initial carries it on to an equal but opposite displacement lah. Note that the time period can be measured lah. So the swing, the one cycle of swing can be measured as period or time period. One full swing from one position to another position and back to its origin position, we can measure its time. It's called as time period. Okay, pendulum is example of periodic motion. One of example of periodic motion. Okay, another example of periodic motion is spring lah, ataupun spring mass system lah. If the mass, sama juga macam pendulum, if the mass is displaced from its original position and released, then force in the spring will act on the mass so as to return it to that position. So dia akan patah balik ke original position. it behave like a pendulum lah, sama macam pendulum, in that it will continue to move up and down, up and down, up and down. The resulting motion up and down can be plotted against time and will result in typical graph of sinusoidal. Kita akan dapat sinusoidal graph. Graph macam ombak tu kita akan dapat dia punya graph like a ombak, like a wave. Okay, okay, this is a typical sinusoidal graph lah. So in sinusoidal graph, we are plotted the amplitude versus time, So from the graph, we can get the amplitude, the size ataupun the magnitude of the displacement of pendulum or spring mass. And also we have the period, one full cycle. What is the rate of one full cycle period? Okay, motion which repeat itself precisely can be described with the following term lah. So daripada sinusoidal graph ni kita akan dapat beberapa term lah. Number one is period lah, ataupun time period, ataupun masa dia. The time required to complete a full cycle, one complete full cycle, is called period. A symbol of T, and is measured in second per cycle. Second, selalunya dalam second lah. Okay, another value that we can measure from this periodic motion is frequency. Okay, frequency is the number of cycle per second. Okay, dalam satu second ada berapa cycle dia boleh buat complete cycle. Pergi, patah balik, pergi balik. Ada anak asal. From one point dia bergerak, patah balik. Okay, berapa kali dalam satu second? Kalau dalam satu second ada 5 second, itulah frekuensi dia. 5 bahagi 5 Hz lah. So unit dia ialah dalam Hz, frekuensi dalam Hz. Okay, the amplitude is the maximum displacement from equilibrium. Okay. Kalau tengok dalam gambar rajah tu ialah amplitude dia. A is the maximum displacement from equilibrium. Okay, ini sinusoidal graph. So from periodic motion, example of periodic motion kita ada spring mass system and pendulum. And then from this system we can make a graph, atau kita plotted a graph, amplitude times ataupun versus time, kita akan dapat sinusoidal graph. In sinusoidal graph we can calculate period, we can measure the period, the frequency, and also the amplitude of the spring mass or the pendulum punya system. Okay. It's example of macam mana dia nak calculate, how to calculate period and frequency lah. So the formula of relation of period and frequency is inversely proportional. So time is equal, T is equal to 1 over F, ataupun F frequency is equal to 1 over T. So from this animation we can see that the spring mass system take 77 second per cycle. Turun daripada asal, turun naik atas 77 second. So 1 over 0.77 we get 1.2987 Hz. Kita dapat 1.2387 Hz. So boleh Kalau kita nak dapat kalau nak dapat period pula, patah baliklah 1 over 1.2987 kita dapat 0.77. Itu period lah. So period dalam second, frekuensi dalam Hz. Ini contohnya lah. So we try to see an animation from this video from www.physicscrashcourse.com.
June 2001, officials in London unveiled a striking new feat of engineering, the Millennium Bridge, a pedestrian bridge spanning the River Thames. It promised to be very useful and it was cool to look at, but it had to be closed almost immediately, because when people used the bridge, it swayed back and forth noticeably due to the force of their footsteps. Undeterred, people kept using the bridge, but as they walked, they began to lean into the swaying to keep themselves from falling over, and that only made things worse. Eventually, the motion of the bridge became so severe that the bridge took on the shape of a giant S, essentially a horizontal wave. The bridge had to be closed and the engineers took nearly 2 years to fix the problem. So what was wrong with the Millennium Bridge? And why didn't the engineers foresee the problem? The answer lies in oscillations. The physics that cause the swaying of the Millennium Bridge has to do with oscillations, or back and forth motion. Or more specifically, it has to do with simple harmonic motion, where oscillations follow a particular consistent pattern. But before we had the Millennium Bridge as a real-life example, physicists often described simple harmonic motion in terms of a ball attached to a horizontal spring lying on a table. While it's lying there at rest, it's in equilibrium. And when you move the ball so that it stretches the spring, then let go, the ball keeps moving back and forth forever. In a frictionless world. That back and forth motion caused by the force of the spring is simple harmonic motion. Now, we want to know two things about this oscillating ball. What kinds of energy does it have? And what's its maximum velocity? To better understand what's happening to the ball, let's start with its energy. As the ball compresses and stretches the spring, both kinetic energy and potential energy come into play. Kinetic energy is the energy of motion, and as the ball moves, there are 2 points, the turning points, where it's not moving. One point is where the spring is compressed all the way, and the other is where it's stretched all the way. And the distance between either of these 2 points and the equilibrium point is called the amplitude. At those 2 turning points, the ball won't have any kinetic energy since it isn't moving. Instead, all of the ball's energy will be potential energy from the spring, half of the spring constant times the amplitude squared. Now, as the ball moves towards the middle, its kinetic energy starts to increase because it's moving faster and faster. And at the same time, its potential energy decreases, keeping its total energy the same. And exactly in the middle of the ball's motion at the equilibrium point, its potential energy goes down to 0. The ball is back where it started, so the spring is no longer pulling on it. Its kinetic energy, on the other hand, has reached its maximum, which means that at that point, the total energy of the ball will be equal to half of its mass times its maximum velocity squared. Now we have 2 equations for the total energy in this oscillating spring, which we can combine into one equation. And if we use algebra to move around its variables, we can start to answer the second question we had about the ball. We wanted to know the ball's maximum velocity, and this equation tells us that it's equal to the amplitude times the square root of the spring constant divided by its mass. So we've answered our 2 questions about the ball on the spring. We know about its energy and we have an equation for its maximum velocity. But there's a lot more going on with this ball than just its energy and velocity. It also has properties like period, a frequency, and an angular velocity, plus its position changes with time. You might recognize those terms because we already talked about them in our episode on uniform circular motion, and that's no coincidence. Simple harmonic motion is actually a lot like uniform circular motion, mathematically speaking. You can see this for yourself if you compare the ball's motion on the spring to an object in uniform circular motion, say a marble moving along a ring at a constant speed. Okay, I admit it might seem like kind of a weird comparison at first. For one thing, the ball on the spring is moving in 1 dimension, while a marble moving along a circular path is in 2 dimensions. But what if you take that ring and look at it from the side? The marble keeps moving along its circular path, but to you, it looks like it's just moving back and forth along a straight line. Not only that, but it looks like this marble is stopping momentarily as it changes direction and moving faster as it gets closer to the middle, which is exactly the same way the ball was moving on the spring. Now let's take this comparison one step further. Let's assume that the radius of the ring is the same as the amplitude of the ball's motion on the spring, and that the marble's constant speed along the ring is equal to the maximum speed of the ball on the spring. In that case, if you did the math, you'd find that the equation for the marble's velocity when you look at it edge on is exactly the same as the equation that described the velocity of the ball on the spring. So let's recall what we know about uniform circular motion to see what it can tell us about simple harmonic motion. We know that the time it takes for the marble to move around the ring once is called the period. We also know that the period will be equal to the circumference of the ring divided by the marble's speed. And the radius of the circle is the same as the ball's amplitude on the spring. So its circumference will be equal to 2 times pi times the amplitude. This this means that the period will be equal to 2 times pi times the amplitude divided by the marble's speed, which again is the same as the ball's maximum speed as it moves on the spring. And we can simplify that equation since we know that the maximum speed of the ball is equal to the amplitude times the square root of the spring constant divided by the mass. So the period of the marble's motion around the ring is equal to 2 pi times the square root of m over k. Now we've also talked about the frequency of uniform circular motion. It's the number of revolutions the marble makes around the ring every second, and it's equal to 1 divided by the period. In this case, the frequency will also be equal to 1 over 2 pi times the square root of k over m. And that'll apply to the ball on the spring too, because the rules are the same. Finally, there's angular velocity to consider. In uniform circular motion, we've described it as the number of radians per second that the marble covers as it moves around the ring. And angular velocity is just equal to the frequency times 2 pi, which means that in the case of the ball on the spring, it's equal to the square root of k over m. So now, with the help of our knowledge about circular motion, we can understand the period, frequency, and angular velocity of the ball's simple harmonic motion as it oscillates on the spring. But there's one more question. How does the ball's position change over time? To find out, we'll have to analyse the marble's motion along the ring again, and the answer will involve some trigonometry. But it's not particularly complicated trig, so it'll be fine. At any given point along its path, the marble will be at a certain angle to the right-hand side of the ring, and the cosine of that angle will be equal to its horizontal distance from the centre of the ring divided by the ring's radius. We already know that the radius of the ring is the same as the amplitude of the ball's motion along the spring. And if you turn the ring so it looks like a line again, you can see that the marble's horizontal distance from the centre of the ring is the same as the ball's distance from the equilibrium point. So the cosine of theta is equal to the ball's position divided by its amplitude. In other words, the ball's position is equal to the amplitude times the cosine of the angle. And we can simplify this equation too. In the same way that distance is equal to velocity multiplied by time, the angle is equal to the angular velocity multiplied by time. So we can write the equation for the position of the ball as x equals a cosine omega t. And when you graph this equation, something interesting happens. It looks like a wave. We'll be talking a lot more about waves in our next 3 episodes, but for now, it's helpful just to see the connection here. For an object in simple harmonic motion, the graph of its position versus time is a wave, which is why the swaying of the Millennium Bridge looked like a wave. Speaking of the bridge, we can now better understand what happened to it. The bridge's shimmy was the result of oscillation, but it was made worse by another culprit: resonance. Resonance can increase the amplitude of an oscillation by applying force at just the right frequency. Kind of like how you can get a kid on a swing set to swing higher by pushing at just the right moment. The engineers of the Millennium Bridge were reminded of that the hard way. When pedestrians on the bridge started to lean into its swaying, they created resonance. They amplified the amplitude of the oscillation. And the engineers of the bridge did account for oscillations caused by resonance when they designed it, but they only considered the vertical oscillations, the kind that would have made the bridge bounce up and down. They didn't realise that they'd also had to factor in the horizontal swaying caused by people walking. So it was only a tiny bit of swaying at first, but it got a lot worse because people were leaning into their steps, causing resonance. In the end, engineers had to apply a series of changes to the bridge to counteract its oscillations. Because if there's one thing you don't want your bridge to be doing, it's the wave. Today you learned about simple harmonic motion, the energy of that motion, and how we can use math of uniform circular motion to find the period, frequency, and angular velocity of a mass on a spring. We also described how the position of an object in simple harmonic motion changes over time. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check out a playlist of the latest episodes from shows like First Person, PBS Game Show, and The Good Stuff. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio with the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
Okay, we try to continue with resonance. What is resonance all about? Apa itu resonance? Okay, everything in this world has its own natural frequency. Contohnya badan kita pun kita ada own natural frequency. Frekuensi natural dalam badan yang mana if if a vibration ataupun satu vibration yang sama amplitude dengan vibration badan kita akan merasa getaran, ataupun we can, kalau sampai kita punya natural frequency, it can also break our body somehow lah. Contohnya glass ni kan. Contohnya a glass of water. A glass of water. Kalau kita jerit into a certain amplitude, the glass will break because our sound made by from our mouth is come from a vibration. Suara yang keluar daripada mulut kita because of vibration. So vibration of molecule of air ni akan transfer to the glass, and if the vibration is equal to the natural frequency of the glass will break. Macam orang dalam opera kan, kalau itu sampai natural frequency of the, contoh mirror kat keliling ni akan pecah. Contohnya kalau dalam aviation ni, kalau awak ingat kapal terbang Concorde. Why Concorde is banned from any airport in the world? Because dia punya speed of the aircraft will create a vibration atau sound vibration that will break the glass of our airport punya glass lah. Glass and mirror lah dekat airport. From the Concorde punya speed tu. Dia punya speed and dia punya frequency of dia punya sound of the engine, they can vibrate. They can send the vibration through the air to the mirror and then break the mirror. That's why it's one of the cause the Concorde aircraft been banned from flying in any airport in the world. Okay, that is rationale lah. Rationale analysis of oscillating system such as pendulum or the spring mass will show that they often obey simple but strict law lah. So the law is the period of oscillation is equal to 2 pi over omega. Macam W. 2 pi over omega. Such motion is often referred as harmonic motion. Okay, resonance. Physics define resonance as a phenomena in which an external force or vibrating system force another system around it to vibrate with greater amplitude at a specific frequency of operation. Kalau awak tengok dalam gambar rajah ni, in a picture in the slide, we can see a turning fork, a wooden box. Ada satu macam penukul will knock the turning fork. So the turning fork will come with a vibration sound. Another turning fork beside it will also vibrate if the frequency of the turning fork is the same ataupun less than the the first turning fork lah. So the second turning fork also will vibrate lah. So the vibration of the second turning fork will make the ball bounce because of the vibration through the air will cause the ball to oscillate ataupun bergerak ke kiri dan ke kanan, menyebabkan bola tu pun bergerak disebabkan oleh frekuensi ataupun disebabkan amplitude of vibration tu. Vibration daripada fork yang pertama ni akan berpindah kepada vibration fork kedua, and then vibration from the second fork akan menyebabkan bola itu terhuyung-hayang pada certain amplitude. Okay, that is called resonance because external force or vibrating system force memaksa another system. Force daripada turning fork, the first fork ni akan menyebabkan another fork pun vibrate pada certain amplitude yang akan menyebabkan ball ni pun akan bergerak pada certain amplitude. That is resonance lah. Itu ialah resonance. Okay, this is a picture of example of resonance lah, video ataupun animation of resonance. Tengok yang on the left hand side, kita tengok kita ada Chinook, helicopter Chinook, which the rotor head ataupun the rotor blade vibrate as the same frequency of our Chinook body. Chinook punya body tu dia ada own frequency lah. So the vibration of dia punya rotor blade dengan gearbox is the same as the body natural frequency that make the Chinook helicopter destroy, because frequency rotor blade sama dengan body of the helicopter. Sama juga dalam picture on the right hand side, kita tengok ada a glass which been put near to a amplifier ataupun speaker. So the speaker produce a sound vibration, produce a sound which vibrate to the air. At the certain vibration, you can see that the glass is warping, macam bergerak, macam berterhuyung hayang. Glass tu macam bergerak. At certain dia punya amplitude, the glass will break. That is resonance. That is resonance. Okay, let's continue to take a look at animation regarding resonance from video source from physics crash course. So let's pay attention to the video.
Topic: resonance. How does sound break glass?
Obviously using a hammer.
Nah. It is because of resonance.
I know. Resonance means to keep calm and balance.
No. Wait, I'll explain. Every object when struck vibrates at its natural frequency. If we make sound having a frequency which matches the object's natural frequency, then that object starts to vibrate. This phenomenon is called resonance.
So, this was the reason why my legs started to move when the music system was switched on.
Oh, just listen. Every glass is made up of different materials. However, all of them have a natural resonant frequency. Hence, when we make sounds which match their resonant frequencies, the glasses start to vibrate. As glass is a brittle material, louder the sound, more violently will it vibrate, causing the glass to shatter into pieces.
Okay, velocity ratio. Velocity ratio or speed ratio or VR in this shortened names. The ratio is a ratio of input to output displacement. Velocity ratio ataupun speed ratio is known as ratio of input to output displacement. Ataupun other name is movement ratio lah. So velocity ratio ataupun movement ratio is equal to input distance move over output distance move. Okay, you can see the distance move by the load in the picture. You can see distance move by the load. So example 2 cm. So the effort movement is more than it because of the fulcrum is near to the load. So the effort movement is bigger. So we calculate it. Example 2 cm to output 10 cm. So 2 over 10 is equal to 1 over 5. That is the velocity ratio or movement ratio. This ratio or movement ratio doesn't have unit. It is a ratio, physical ratio, to see the mechanical efficiency of an item ataupun mechanical machine. Okay, let's take a look at the question, example 1. If the effort move 5 meter, so kita bagi satu effort, kita tekan 5 meter move, while the load, ada berat kat hujung tu, move 1 meter. What is the velocity ratio ataupun movement ratio? Kita kena ingat, the velocity ratio is equal to input distance per output distance. So the input is the effort. So 5 meter over 1 meter is equal to 5. Okay, effort 5 meter, load 1 meter, so equal to 5. There has no unit. Okay, let's take a look at mechanical advantage. Okay, what is all about mechanical advantage? Okay, mechanical advantage, the greater the mechanical advantage, the greater is the load that can be moved by a given effort. So, contoh satu machine tu, satu tools tu, dia punya mechanical advantage is bigger, besar. Mechanical advantage dia besar. So, the load yang kita boleh angkat dengan effort yang sedikit. Contohnya kita punya, awak ingat jet kereta, jet hidrolik lah. So, awak tekan sikit saja. Tapi awak punya load yang awak yang angkat tu berat. Kereta yang awak angkat tu besar. So mechanical advantage of the jet hydraulic is bigger. So because while you give a less effort, but you can lift ataupun you boleh angkat load yang besar. Awak boleh angkat kereta dengan effort yang sikit yang awak tekan, tapi awak boleh angkat load kereta yang besar. That is mechanical advantage. If the machine use a small effort, guna small effort je to move a larger load, satu benda yang berat, it is said to have a good mechanical advantage. Okay, mechanical advantage ataupun force ratio is equal to load over effort. Load over effort. Okay. Some of the simplest mechanical advantage device used is levers lah. Levers, pulley, gear. Itu adalah example of mechanical tools ataupun mechanical device. Boleh dekat ni Okay, we continue. If you have any question, you can let me know through our chatting here. Okay, let's take a look at another example for mechanical advantage. An effort of 10 Newton, ingat 10 Newton, effort dia 10 Newton, is used to move a load 50 Newton. What is the mechanical advantage of this lever? Kita kena ingat mechanical advantage terbalik pada velocity ratio, iaitu load dia per effort. So load kita 50 Newton, dengan effort 10 Newton kita boleh angkat. 50 Newton load dia. Load 50 Newton, effort kita 10 Newton saja, tapi kita boleh angkat 50 Newton tu. So, load per effort 50 over 10 is equal to 5. There are no unit also because it a ratio. Kalau ada NN, Newton bagi Newton pun akan dapat hilang lah, tak ada unit dia nak ratio. Okay, kita tengok, take a look at example of mechanical machine. Mechanical machine ataupun mechanical tools yang selalu kita guna. Salah satunya ada lever lah. Kita tahu kita ada lever, pulley, gear. One of it is lever lah. In physics, a lever is a rigid object that is used with an appropriate fulcrum ataupun pivot point. Fulcrum atau pivot, awak ingat jongkar-jongkit kan? Kalau ada jongkar-jongkit, kita ada saw. Jongkar-jongkit kita ada satu-satu kat tengah tu. Yang tengah tu kita panggil pivot point ataupun fulcrum. Tengah tu panggil pivot point ataupun fulcrum. Okay, to multiply the mechanical force that can be applied to another object. The lever allow less effort to be expended to move an object through a distance lah. This enhancement is also termed mechanical advantage. There are 3 classes of lever. So dalam lever ni dia ada 3 class that we come across in our everyday life. So lever ni banyak contoh lah, tapi dia bagi pada 3 jenis ataupun 3 classes. Okay, kita tengok kelas apa yang ada pada lever ni. So ada 3 kelas, the first order, second order and third order. Apa bezanya? Ialah apa yang ada di tengah-tengah dia ataupun position fulcrum dia kat mana. Apa yang berada di tengah-tengah ataupun position fulcrum. Example 1, first order. Kalau awak tengok first order kat sini, fulcrum dia berada di tengah-tengah. Fulcrum berada di tengah-tengah. Load dan effort di kiri dan kanan. Tak kisahlah kiri atau kanan, left or right also. Example of first order, kita tengok hammer lah. Hammer, kita ada pemegang tu effort kita. Load kita di hujung tu paku, and di tengah-tengah kepala tu claw hammer head tu ialah kita punya fulcrum. Okay. Another one, kita punya plier. Kita tengok fulcrum tu kat tengah-tengah, dia punya joint of the plier tu kat tengah-tengah. Effort kita tekan plier tu, tempat pemegang tu kita tu ialah kita punya effort. Kita load kita dekat hujung tu yang kita nak pegang tu kan, kita kepit pak. Load ini kita punya load, kita punya pemegang untuk load kita. Belakang kita punya effort, tengah-tengah ni this side is fulcrum. Itu first order. First order fulcrum dia dekat tengah. Okay, second order, apa yang kat tengah? Ialah load dekat tengah. Apa yang ada kat tengah? Load dekat tengah. Contohnya wheelbarrow. Wheelbarrow kita tengok kita angkat kan. Tempat yang kita angkat tu ataupun apa orang panggil 3 roda. Untuk ni lah, untuk baju simen semua kan. Wheelbarrow ni dekat hujung tu yang kita angkat tu ialah kita punya effort. Kita punya load dekat tengah, kita punya batu ke simen ke kat tengah. Hujung tu dekat roda tu ialah fulcrum. Itu second order. Satu lagi adalah nutcracker. Nutcracker pun sama juga, load dekat tengah. Kacang tu kat tengah, ujung tu fulcrum, and effort yang kita tekan tu lah, itu second order. Dan another one is third order. Third order, effort kita kat tengah. Tadi first order, fulcrum kat tengah. Second order, load kat tengah. Dan third order ialah effort kat tengah. Okay, contohnya human arms lah. Human arm, tangan kita. Ini tangan kita. Tangan kita. Dekat tangan kita, hujung tangan kita ni ialah load. Sebab kita selalu angkat barang load. Okay. Tengah kita ialah kita punya effort kita. Effort kita. Hujung ni, muscle kita ni. Lamuk mana ni? Okay, ni muscle kita ni. Ini kita punya effort. Muscle kita ni effort. Hujung kita ni, ni kita ni ialah kita punya fulcrum. Fulcrum yang boleh gerak ni. Muscle kita yang effort kita ni, muscle. Hujung ialah load. Another one is sugar tongue. Sugar tongue ni ialah ujung dia fulcrum, tengah dia effort, ujung sekali ialah load. So this is three class of lever. Three class of lever. Another mechanical tools ataupun mechanical machine is pulley lah. Benda-benda yang memudahkan kerja kita. A pulley is a wheel on an axle that is designed to support movement of a cable or belt along its circumference. Pulley are used in variety of ways to lift, load, apply force and to transmit power. Sama jugalah macam dekat lever. Kita guna untuk apa lever ni? Ialah untuk lift, load, untuk apply force dengan transmit transmit power. Sama juga. Pulley pun sama juga macam lever. Another one mechanical machine is gear lah, yang memudahkan kita kerja. So tadi kita belajar pasal velocity ratio, movement ratio and mechanical advantage. All is being used by these three mechanical machine: lever, pulley and gear system. Okay, a gear is a rotating machine. Kita tahulah, awak semua tahu gear ni is a rotating machine. Macam bicycle kita ada gear, engine kita pun ada gear, gearbox kita pun ada gear, semua tu ada gear lah. A gear is a rotating machine part having a captive or cogs which mesh with another tooth part in order to transmit torque lah. Okay, two or more gear working in tandem are called transmission lah. Transmission. Okay, this is an example of gear lah. Kita ada spur gear, kita ada straight and bevel gear, spiral bevel gear, worm gear, hypod gear, planetary gear set ataupun sun, and heliaxical gear and herringbone gear. So all this type of gear has been used by our machine ataupun mechanical machine to transmit power, to lift, load and other things. Okay, I think that's all for today. Thank you very much for your time watching my video and also discussing with me throughout this video. So anything you can PM me to ask question. We will see you in the next session. Thank you very much. I will leave you an assignment. Please do and submit to me during the time interval that been given. Okay, thank you very much. Assalamualaikum.